So in this video, we're going to talk about least squares regression line, actually how to calculate or find it by hand using information from the data set, how to find the variables B and A for the least squares regression line. And then we're going to talk about influential points and outliers and how they affect everything that has to do with the line and correlation, and then coefficient of determination as well. So for the least squares regression line, we've talked about how it's y equals a plus bx. There is a way to algebraically find a and b. So b can actually be found by this, r times the ratio of the standard deviation of y, standard deviation of x. So this right here, your r value, that's from the -1 to 1 range. sy, or s sub y and s sub x, that's standard deviation of each data set, each list in the stat menu. And then actually to find a, your y-intercept, it's the mean of the y times, or sorry, minus b times x, mean of x. And this is because, something I haven't talked about yet, this is because the least square regression line must pass through this point, x bar, y bar. So that's the mean for the list for x and the list for y. Every single least square regression line must pass through that point. It's the fact of the math. And because of that, we're allowed to find a using this. This is just like any other algebra problem. Back algebra 1, you're finding the equation for slope-intercept form. They give you a point, 2 points, or a point in the slope. It's the same math involved here. This is the point that we're giving you, and you should be able to find a and b if I give you r as well. Some notes on this. If r is equal to 1 or -1, this means that a change in standard deviation of x will be the same change in the standard deviation of y. So 1-to-1 correspondence there. It'll follow the line continuously up, and that's when you have that perfect data set. Every single point hits the line exactly. However, the problem is we don't usually have those. We don't have perfect data sets. We have associations that are, the residuals are positive and negative. They're all over the map. They're scattered throughout the scatter plot. So most of what we do, or most of what we measure, will be between -1 and 1. So what happens there, if this number if this number is less than 1 or larger than -1, it's now a fraction. That means if I change, one standard deviation to the right, this standard deviation does not change a full click up. So if I go 1 standard deviation to the right in the x direction, I don't go a full standard deviation up. It only happens when you have a perfect r value of -1 or 1. But like I said, most of what we do here, it's in between there. So when you make a full change in the x direction, 1 standard deviation, it won't go up a full standard deviation in the y direction. So what happens here is the closer and closer you get to 0 for your r value, the less and less accurate this line will be. And that's because when you change your slope to fit the r value like this, and the r value is very small, every time you change an x standard deviation, this doesn't change as much. This is what's called the regression to the mean. This will just become the mean, as is the less associated it gets. So when we say an increase in 1 standard deviation, in the x direction, means there's a change in the y direction less than 1 standard deviation. And at a certain point, this is important, if R is close enough to 0, meaning that if it's a weak enough association, then Y bar is a better approximation or predictor than Y hat. If your R is small enough, your equation producing your predicted Y value is less accurate than actually just your mean of all your Y values. And this is a very basic calculation, and we use it only in terms when we have a scatter plot that's clearly showing us very little correlation or weak correlation or no correlation at all. There's a good run through in the textbook, 183, 184. It's a good discussion about how this actually works in more in depth, and it actually gives you a graph too. It shows the lines for mean, standard deviation in both directions on the graph, vertically and horizontally. Give it a read, and you'll get a better understanding of what's going on with the equation and what happens when what happens when R is close to 0 or R is close to 1 or negative 1. So page 186 to 188, we have numbers 1 through 3 under correlation and regression wisdom. We're bringing both of these ideas together. So first, distinction between explanatory and response variables is important with regression. Not so much with correlation. Correlation doesn't care about variables. It cares about numbers, and that's it. It just wants to do z-scores and multiply them together and sum them up and can find the average z-score product. That's all it wants to do. Regression, though, it's very important, the variables, which one is x, which one is y, because that you're doing residuals. That's the vertical distance, so there is a big difference when switching them around. So this more wisdom here. Correlation and regression lines describe linear relationships. And that's it. No other types of relationships are allowed to be described by correlation and regression lines. This has been said multiple times throughout multiple lessons, but it bears repeating. It's so very important. People try to use R and R squared and least square regression lines for data that's clearly not representative of a linear relationship. There's lots of relationships out there that are nonlinear. They could be polynomial, they could be exponential, logarithmic. Those are perfectly fine. Those relationships exist. You just can't use least squares regression line for them. You can't use correlation either. They have their own tools out there. Correlation and the least square regression line are not resistant. Outliers affect both of these things, and we'll talk about that very soon here. But taking up a single point out of the data set changes your equations for R, R squared, and the least square regression line drastically. So they are not resistant because they involve mean, standard deviation within their equations. And lastly, again, it bears repeating, association does not imply causation. Finding an R value or an R squared value that's pretty high, and that's the only thing you do, is not good enough to prove causation. Association is important, but if you're actually trying to state for sure that one variable causes the other, you need more than that evidence, just the association. Okay. The outliers and influential points, you're going to be able to describe the slope, y-intercept, standard deviation of residuals, and R squared, how they're influenced by outliers. So outliers, it's an unusual point. It lies outside the overall pattern. Of the other observations. if you're an outlier in the y direction, even though you are an outlier, you are often not very influential. There's influence there, but when you're speaking in terms of the y direction, since we do residuals in the y direction, if you have lots of points underneath the outlier, it's not going to affect the sum that much. An influential point, however, is a special type of outlier. It's influential because removing it would markedly change the result of a statistical calculation. Usually in the x direction. And this is because it pulls in that direction, the line. So in the x direction are often influential for the least squares regression line. And we'll look at a couple of examples here. This right here is a point that is an outlier. It's above the rest of the pattern here. But do you see how it's in the y direction and we got all this data underneath it? Since we have residuals already balanced out there, if I take this out or I put it in, the line maybe will go from here to maybe there. Not a whole lot of change. It still pulls it up a little bit, but it's not very influential. So the outlier we'll say is 3, 10. It's unusual in the y direction, but due to the points below, the least square regression line wouldn't reduce the residuals much without the point. Okay. This point, however, right here, is very influential, right here. In the x direction, you'll see there's a big gap here. It's way outside the pattern. So if that weren't there, you might imagine the line would probably look something like that. But once you add this in there, this line is going to be pulled this direction because of that point, because it's in the horizontal direction. So you might see the line do this. I'll do a dashed. Something like that. And you can see how drastic that would be of a pull. This gets pulled on all the way here just because this one outlier point in this direction, in the x direction. So this is a 10, 3. It's unusual in the x direction. And to minimize the vertical distances, the least square regression line will be pulled down. So this slope's going to decrease by quite a bit. And since this statistical calculation has changed by quite a bit, this is going to be an influential point. So because this line has changed so much, we call it an influential point. This one's not very influential because you look at the line change, it's not that big of a deal. There's a couple of examples, or this example from the book here, where they have children in the study, the age at first word in months, plus the adaptive score, it's a test score. Just talking about the scatter plot between the two variables. And there's a couple influential points here. We have child 18 and 19. This one here, without child 18, without child 19, they have 3 lines. The middle one is just the least square regression line with both of them in there. You look at child 19 right here. Look, it's far above the data, but in the y direction. There's lots of data down below, and as to where it's not going to be, influencing in the y direction because there's so much data right below it. So this point right here, child 18, you'll notice that in the x direction, it's got a big difference here. And the two other lines are given without those childs 18 and 19. So look at child 19 without it. Look how much the line changes. Not that much. You probably couldn't tell the difference if I gave you two pictures. However, if you take out child 18, the one right here, you take it out, this is what happens to your line. Look how much it moves up in this direction. This point was pulling the line down when it was in. As soon as I take it out, the line moves back up, and therefore your statistical calculation changes quite a bit. Also, look here at the R values. So with all 19 children, R is negative 0.64. You take out child 19, it's negative 0.76. It gets slightly stronger, but not a huge difference. If you look at without child 18, sorry, R value changes quite a bit. Your association gets a little bit different, and your equation changes a lot. If you look at the slopes here as well, negative 1.127, negative 1.193, and then 0.779. These two are rather close. This one is not. So this would be your influential point. This would be your not very influential point. All right, last part of 3.2 is calculating the least squares regression line without a calculator. We kind of talked about the equations already, but I'll rewrite them down. Y hat's going to be equal to a plus bx. Your slope b can be found by doing r times the standard deviation of y divided by the standard deviation of x. And then the y-intercept, because it goes through point x bar comma y bar, this is your equation to find your y-intercept. So in this example, it says use the following information to calculate the least squares regression line. This is what your calculator does. So x bar is 24.76 centimeters. The standard deviation of x is 2.71 centimeters. Y bar is 171.43 centimeters. The standard deviation of y is 10.69 centimeters. R is 0.697. There's no units for R, remember that. This right here shows that it's a positive association and it's quite strong. You'll notice that I have R, S, Y, S, X. I have all three of those here, and plus the two means. All the information I need is to find is right here. First, find B. So plug in R, 0.697 times the standard deviation ratio, so 10.69. That's the standard deviation of Y, divided by the standard deviation of X. You get 2.75 for the slope. A, that's going to be your mean of Y, so 171.43, minus your slope, 2.75, times your mean of your X, that's 24.76. That's going to be equal to 103.34. So your your least squares regression line is y hat equals 103.34 plus 2.75x. So I'm going to be able to give you all this information, and using the equations that are going to be given to you, you should be able to do this basic algebra to find the equation for least squares regression line. This is harking back to algebra 1, where you have to find the slope first, and then find the point for the y-intercept. You plug both those numbers in, and you get your equation. So just remember that we have two different types of outliers with scatter plots. We have influential points, and we have not influential points, just basic outliers. It depends on what direction it is in. If you have it in your y direction and there's points underneath, that's not going to be very influential. This point here, though, in the x direction, you'll notice the change in the least squares regression line. It changes quite a bit. This point pulls it down some. So keep track of those different types of influential points, or sorry, outliers. Some basic knowledge about correlation and regression. We talked about there's a distinction made with regression between the two variables. Correlation, there is not. The correlation does not care about the variables, just the numbers themselves. These two tools are used for linear relationships only. Do not try and use these for polynomial or logarithmic or exponential. Correlation and least square regression lines are not resistant. They are affected by outliers, so keep that in mind. We're looking at a scatter plot. Association does not imply causation. This is not the only thing you would need to actually use in order to prove causation. It takes a little bit more than that. It is a good place to start, though. Again, if you want more details about this discussion about the least square regression line equation and how when you have an R value between -1 and 1, it affects your regression to the mean of the standard deviations, please look at page 183 and 184 for that. R squared coefficient determination is just a square of your correlation coefficient. Its range is 0 to 1 instead of -1 to 1 because you're squaring all these numbers. So all these negative numbers to the left of 0 become positive in this range. There's actually an equation to calculate R squared using the square of the residual sum divided by the square of the y minus y, the deviations, 1 minus that. R squared, say the following when you see it: that much percent of the variability is accounted for by the least square regression line. So both have a sum of residuals squared, both equations for standard deviation residuals and the coefficient determination. Those are a big deal, the residuals. And they both describe how well a line fits the data. Both of these variables describe it. One does it with units and one does it without units whatsoever.